А завершить трансляцию я вот здесь нажму. Отлично. И завершить трансляцию. Good afternoon, everybody. We start lecture on biophysics. You can see this at the slide. The lecture on the course on biophysics is me, Associate Professor Natalia Pronina. Today and now we start the lecture Physics Basics of Acoustics and Ultrasonic Scanning Implementation in Medicine. The lecture goal is the mechanical waves specification and physical factors in context of its human body functional state influence and implementation for diagnosis. It is the goal of the lecture. And what are the objectives? A mechanical wave motion parameters nomenclature review. Number 2, physics aspects of human structures, ultrasonic scanning technology, and human ear sound perception physics aspects. These are the objectives of the lecture. And look here, you can see the points for the review of this lecture. First of all, let me introduce mechanical wave motion physics basic aspects. The next, it will be the ultrasonic scanning technology of human structures of 3 modes. A, amplitude scan mode, B, brightness scan mode, and the Doppler scanning system will be considered. And under number 3, the point for our discussion, that is under number 3, is the ear sound perception physics aspects. After that, we summarize, we do conclusion, based on that lecture material will be represented, and I give you some clues where you can find the information to add, to contribute that material that will be introduced for you. And let's start from the first point. It is the introduction. Look here, let's first of all define that the beginning of the mechanical wave motion. What is this actually? Actually, we should start from the definition of the processes that are termed as oscillations. And what is the definition of that processes? Processes that are repeating at the same intervals is called vibrational ones or oscillations, independently on their nature. And in particular, we can talk about a mechanical vibration. Mechanical vibration or oscillation is the process when an object moves back and forth repeatedly over the same path. It is said to be oscillating or vibrating. So you can see that a mechanical vibration or oscillation, it is the kind of mechanical motion. you know that kinds of mechanical motion as translational motion, circular, rotational motion. This adjective as not adjective, but this as vibration is identification of the kind or specific kind of mechanical motion. Look, we can say about two types of mechanical oscillation. The free oscillation, the oscillation of a body or a system with its own natural frequency and under no external influence other than the impulse that initiated the motion. This is said to be free oscillation. Let me pay attention that this is done with the vibrating system own natural motion frequency. What is the meaning of these two adjectives as own and natural? These emphasize stress that frequency of the oscillation in this case is determined by the only parameters of the oscillating system. And one more kind of the oscillation, forced oscillations. When energy is fed into a vibrating system, a system is said to be undergoing forced oscillations. And in this case, the frequency of the oscillations of the system equals to the frequency of the forcing. Equals to the force subjecting the system frequency. And what is the task for the physics to describe any kind of the process, to quantify the process, to characterize that process of the interest by quantitatives, by parameters that might be measured or might be calculated from the physics laws determining the relations between the parameters. And the oscillations are not exceptions from this. The task for us is to quantify, the task for physics is to quantify, to describe certainly concretely by strong measured parameters that kind of the motion. And let's consider the simplest situation of the oscillation. It is the harmonic oscillation, simple harmonic motion. Look, you can see here the examples of two simplest oscillating systems. You can see the fixed spring of the elastic coefficient K that is fixed at one end, and at the opposite end is attached to the body of mass M. And this simple pendulum, it is the inextensible rod with the body at its end and the opposite end of the cord is fixed as well as the spring. What is the motion these two may be set into? This is the kind of translational motion. Look, when the body, this body is deflected from its original equilibrium position, it will come back to this position because of the subjection by elastic force exerted by the spring. And this motion will be along the only one line. We draw that line and add arrow. It becomes the x-axis. And in this configuration, we can describe this motion as the change with time, the coordinate x measured along the x-axis. Let me pay your attention that this kind of the motion is the kind of translational motion, and all particles go through the same pathways, and all characteristics, all particles are of the same magnitude. So consequently, it is not necessary to investigate, to study the motion of all particles of the body. It is enough to take the only one point. Conveniently, it is the center of mass, and investigate, research the motion of that particle. Other particles descriptions, particles motion descriptions will be of the same style, of the same parameters. And this kind of the vibrating oscillating system motion is of the same character, but in this case we take the x-axis in horizontal direction, and when we consider very small magnitudes of this angle of the deflection, it might be said about the change of the position measured by the change of the x measured along that horizontal x-axis. So, and by how we can quantify, describe these kinds of the motion? By this dependence of the coordinate on time. This becomes to be the equation of motion, and this, you can see, includes parameters of that kind of motion. This is the maximum deflection of the body from its equilibrium initial position. This is the frequency, the number of the repeating of the motion within time of 2 times pi seconds. So, and what else? This phi with the low index is 0. It is the initial phase, oscillation initial phase, determining the initial position of the vibrating of the body, initial for the moment when this oscillation starts to be observed. And after that, you can see that equation of motion describing without any word, that identifying without any word that kind of the oscillation or that kind of the motion, that is mechanical oscillation. Look, let's come back a little to this as the natural own frequency of the free oscillating system motion. You can see for this vibrating system, oscillating system, the circular natural frequency is determined by coefficient of elasticity coefficient of the spring, and mass of the body attached to the spring. And here you can see that the for the simple pendulum, the frequency, natural frequency, is determined by the length of the cord, inextensible cord, and the gravitational acceleration at the place where this vibrating system motion is observed. So, and what else? These are parameters: period, it is just the nomenclature of the nomenclature of the parameters of the oscillations, mechanical oscillations. The period is the time required to complete one full oscillation. Frequency is the completed oscillations number per unit time. And as it was mentioned already, free oscillations frequency. Free oscillations frequency. And one more should be mentioned here, this phenomenon as the resonance. Resonance, what is this? When a frequency of an external force equals to a vibrating system free oscillations frequency, and amplitude is the largest. And in this case, it is said the system is to be at the resonance. And look, when we talk about mechanical motion, we should take in account, we should remember about energy that is required to this for the system to move. But also one more kind of energy should be taken in account in this particular case. It is the energy, potential energy, the energy of the position. Both are in progress. The position and the motion, meaning the velocity of motion. Both are changing. So consequently, at any instant of time, at any moment of time, the total energy carried, stored into the vibrating system is of two kinds, kinetic energy of motion and potential energy of the position. So, and when we ignore, when the friction is the negligible, we can say that this energy is stored at this system and continues to be of the same magnitude when system is set into the oscillation. And look, the magnitude of this resultant energy is of this value. You can see this energy is determined by the angular circular frequency of the oscillations and amplitude of the oscillation of the vibrating system. When we talk about this weight on the spring, we obtain absolutely same equation to calculate the total energy that is stored and is converted from one type to another, from kinetic to potential and vice versa. This energy, and we can generalize this dependence of the energy stored into any vibrating system, mechanically vibrating system, oscillating system, that is determined by the circular frequency of the oscillations and the amplitude of the oscillations of the particles. Oops, not of the particles, but of the oscillating system. So, and look here, where you can see the example of one more oscillating, not system, but object. What is this? It is not the system of two bodies as it was at previous our discussion, but it is the single body, it is the piston that is forced. Consequently, it oscillates with the frequency of the force applied to it. And where it is moving? It is moving into the cylinder that is filled with the air. Cylinder is opened from one end, and consequently when piston goes into the cylinder, it compresses the air particles. When it goes back, the rarefaction area is developed, and after several oscillations of the piston, when we stop this process and make the instant picture, we obtain this distribution of the pressure into the air, into the cylinder. And this may be represented as this graph. In addition to the atmosphere pressure of the air, this piston pressure is added. And by that means we can see that distribution this P with the index 0, it is just atmosphere pressure, and this extra pressure provided by the piston when it goes into the cylinder, and at the moment when it stops into the cylinder, the pressure on the air becomes the greatest. After that, it goes back, and the rarefaction is developed, and pressure becomes the lowest, and so on and so on. We can represent this distribution of the pressure by this graph as the periodic change of the pressure with the distance along the axis of the cylinder and time. So, and when we continue to observe the motion of the piston, we can see that these areas, rarefaction and compression, are going through the air into the cylinder with particular velocity. And let's look from one point of view on this process. Look here. These are particles of the air. In particular, this one that is in direct contact with the piston. It struck by the piston, it forced by the piston, and as any force, the force from the piston sets the particle into mechanical motion. Particle is surrounded by its neighbor. Any particle that is at contact with the piston so is surrounded by the nearest neighbor. And these particles that are in contact with the piston strike in turn their nearest neighbor. And the relation between the particles, the linkage between the particles may be reconstructed as the spring linking, connecting these particles. So that is why through this deformation of the spring, the force from the piston is conducted to the nearby particle, and from that particle, because of the same connection of this particle neighbors, this force is conducted to the next particle, and so on and so on. And all particles by that means are set into the motion. What is the kind of the motion? It is not translational motion from one end to the opposite end, but because of this connection between the particles, all particles start to oscillate around within relatively to its equilibrium rest positions. And this is done with the same frequency as the frequency of the oscillation of the piston. So that is why we can see the example of two forced oscillations, the forced oscillations of piston and the forced oscillations of the particles of the air. In this particular case, filled the filling the cylinder. And look, as at any situation of mechanical motion, we can write down motion equation to be oscillation. This dependence on coordinate, in this case the y coordinate axis was chosen, and this change with time of the y coordinate motion equation in this harmonic forced oscillation is of the simplest shape, of the simplest form. And you can see how small is the amplitude of the air particles oscillations. Amplitude is of order of their diameters of minus 11 order of 10 meter only. And look, now you can see that we can describe that kind of the motion of the particles of the air as the kind of the energy transmission through the air that is provided by the mechanical energy, by the source of mechanical energy. It is the vibrating piston. And this process of the transmission of the energy into the media without noticeable motion of the substance of the media is termed as mechanical wave. Mechanical wave, it is the transmission of mechanical energy into the medium. So this is just a definition, explanation of that physics phenomenon. And look, we can classify, we can separate mechanical waves into three categories, into three classes, into three kinds, three types: transverse, longitudinal, and surface waves. The criteria for this is the relative directions of the wave propagation and the direction of the vibration of the medium particles. In a transverse wave, particles of the medium vibrate, oscillate up and down, perpendicular to the direction of the wave. In a longitudinal wave, particles of the medium vibrate back and forth, parallel to the direction of the wave. And in a surface wave, particles of the medium vibrate both and down and back and forth, so they end up moving in a circle. A surface wave is a wave that travels along a surface, separating two different media. You can see air and water, and this kind of the vibration of the water particles at the water surface are set into the surface wave, are set into that kinds of vibration as both an up and down and back and forth, and by that means the surface wave is developed. And you can see here the nomenclature of the mechanical wave, nomenclature parameters, nomenclature of mechanical wave parameters. And what is that characteristic identifying the mechanical wave? It is the wavelength. What is this? It is the distance of the transmission of mechanical wave, the distance of the transmission of mechanical energy within time of one completed oscillation of the particle of the medium. And one more explanation, definition of the wavelengths may be given. Look here, you can see here the instant picture, the picture at the moment of time of the placements of the particles of the medium where the mechanical wave goes through. Look, it is the place of the source. It is the vibrating object originating, initiating vibrations, oscillations of the medium particles. And when we make the instant momental picture, we obtain that distribution of the positions of the particles into the medium at any all particles are at different positions dependent on the distance from the wave source. And you can see that some of the particles are at the maximum distances from their original equilibrium positions. They are deflected at the largest distances, and this is termed as the wave crest. And the distance between the nearest wave crests is considered as the wavelengths. What is this? This is the distance between the particles, nearest particles that are at the same positions into this space. It is not obligatory that these should be the maximum deflecting particles. It might be any, but they should be at the same positions. At the same positions. So, and this is just the wavelengths. And you can see the relation between the velocity of wave propagation, the frequency of the wave that equals to the frequency of the particles oscillations, and wavelengths. This is just the relation. So this is not too long a list, or it is not of the wave parameters. You can see what are the major of them. Describing just the specificity, quantifying just the specificity of that kind of mechanical motion, actually. And look to say about the motion of the particles into the space the wave goes through. We can write down this wave equation. What is this? This identifies, determines the position of particle, any particle of interest into the medium at a moment of time that is of interest. Look here, this position, as it was said already, depends on the distance from the source and changes with time. So the coordinate, white coordinate of the particle into the space crossed by the wave depends on its direction, on its distance from the source of wave and time. It is function of two parameters. And you can see this wave equation using this analytical formula. The position of any particle, what does this mean? At of any particle at a particular distance from the source, at any instant, at any moment of time, may be calculated. It is just the principle, physics principle, to describe the processes. So you can see, first of all, physics described the processes of the system oscillation as the change of coordinate of the body of the oscillating system. And in this particular case, physics describes the behavior of the particles of the medium wave crosses as they change of the position with time of that particles relatively to their original positions, and this depends on the distance from the source of the wave. Very good. And look here, these are the examples of mechanical waves, generation and registration. Vocal chording is the source of the sound. And after that it goes, this vocal cordy is the vibrating system. So, and this system disturbs the air into throat, and after that this disturbance, vibrations go through from the throat into the through the air, reaches the ear of listener, and you can see that vibrating system, vocal cordy, the medium that is required to conduct mechanical energy, and perception of this energy by the ear. And in this particular case, look, what is the source of mechanical wave? It is the wall of the artery that is closest to the skin at this wrist position, and by palpation, by the receptors on the ends of the fingers. These mechanical wave may be recognized, and this vibration of the artery wall is in accordance with the rhythm of the heart contraction. And so by that means, this may be used to count the number of heart beating per particular time. This is just the palpation of the pulse. Palpation of the pulse. Non-invasive diagnosis actually of the heart function. Very important information of the heart function. This is the number of the heart beating per unit time. And the next, it is the energy characteristic, because you should remember what is the mechanical wave. It is the transmission of the energy through the space, through the media. So consequently, we should say about energy carried by mechanical wave. And look, the energy carried within this time is divided by the time, and the flow of energy becomes to be energy characteristic of the wave, mechanical wave. When we calculate how much energy is carried through the unit area of the surface mechanical wave goes through, we obtain the convenient energy characteristic of wave, that is the intensity. And you can see the intensity, the energy carried per unit time over unit area, uh, is dependent on the amplitude of the oscillations of the media particles and their frequency, and the frequency of their oscillations and velocity of propagation of the wave into the particular media. And one more characteristic should be mentioned, but this is prescribed to the medium. It is the medium acoustic impedance. It is the measure of the ability of the medium to conduct, to transmit, to carry a mechanical wave energy. To carry mechanical wave, to transmit mechanical energy. So it equals to product of the density of the medium and velocity of the wave into that medium. Velocity depends on the character of the medium. Would it be solid, would it be liquid, would it be gas? The largest velocity is in solids. The middle velocity is in liquids. In particular, for the soft human tissues that are rich of the liquids, we can take the mechanical wave velocity equals to the velocity into the water, that is 1500 meter per second. And consequently, this is a velocity for the gas, in particular for the air. This is around 3 times less, equals to 330 meter per second. And you might remember the density of water, 10 to the power 3 kilogram per meter cubed, and air is of density 1.29 kilogram per meter cubed. You can see how differ these two, meaning their ability to transmit mechanical energy carried by mechanical wave. So their impedances are very different in magnitudes. And look here, a wave interaction with the medium. We start from this phenomenon as the reflection. When a wave meets a change in medium, what is the change? The change in media acoustic impedances. The wave splits. What does this mean? Partly energy is reflected by the surface separated into different media, and partly energy crosses that surface and goes to the second medium. And in the simplest case of the normal incidence, the reflection coefficient may be calculated using this formula. And you can see the larger the difference between the acoustic impedances, the larger reflection coefficient would be. So, and it is greatest equals to the 1, to the contact of the air and water. From this surface separating air and water, the sound or ultrasound is totally reflected. Energy comes back to the first medium and doesn't cross that surface separating two media. And look, you can see that example where these physics phenomena as reflection, in particular total internal reflection, is implemented. It is the stethoscope to do what? To auscultate the vibrating, oscillating structures inside the human body, in particular the heart, are the sources of mechanical waves that go from inside up to the skin, and after the sensitive membrane of the oscilloscope initiates the vibration of the air, filling the tubes, rubber tubes or plastic tubes of the stethoscope, and this mechanical energy is carried by air into the physician ear, and by that means the physician to be experienced enough can make conclusion about state of that or another structures inside that are producing mechanical waves. It might be lungs, for example, it might be the heart, for example, something like this. You can see physics phenomena, reflection is implemented in practice. And attenuation. It is understandable when the mechanical energy crosses the media. It is, what is the mechanical wave? It is the mechanical energy. So the energy is given to the particles, and in particular, partly this energy is converted into the random thermal motion of the particles. So, and this is just the loss of the mechanical wave energy, and this is reflected by attenuation. Or what is this attenuation? It is the diminishing, decreasing of the intensity of the mechanical wave with the distance. The wave goes through, travels through the media. And the change of the intensity is exponential with distance. The mechanical wave crosses into the medium, and this attenuation coefficient is dependent on the medium as well as the frequency. The higher frequency, the more attenuation. So the mechanical wave with the larger frequencies are attenuated in greater extent with respect relatively to the mechanical waves intensity of lower frequencies. And one more phenomenon should be mentioned. It is the acoustical pressure of mechanical wave of intensity I traveling in medium of acoustical impedance Z produces pressure on the surface wave falls on top. In case of the flat surface that is positioned perpendicularly to mechanical wave velocity acoustic pressure may be calculated by this formula. It is intensity, it is a mechanical impedance of the medium, and this formula is for, it is not power of mechanical wave, it is just the pressure on the surface mechanical wave strikes. And look, now we will use this. But before we do this, let me represent you one more physics phenomenon. That is the Doppler effect. Doppler effect. Look, this effect is illustrating here. What is this? This is the situation when the receiver or the source of mechanical wave are in relative motion, and you can see what happened. The Doppler effect is apparent change in frequency registered by an observer when there is a relative motion between the source and observer. So moving object changes the incident wave frequency. Measuring the frequency shift, the moving object velocity can be determined. This is illustrated at the diagram. You can see how frequency is changed when the source is moving towards the observer who is at rest. This is the new frequency produced by that motion. And in case of source motion away from the observer who is at rest, the velocity, the frequency registered by observer is of this magnitude. This is the original frequency of the sound produced by the source. And this apparent frequency registered by the observer. Motion of the source that is moving with the velocity v source s relative to the observer alters the wavelength and frequency of sound waves. So this Doppler effect is the base for the one of the diagnostic modes we will consider. And now, finally, let's take this classification of mechanical waves. The criteria for this is the frequency. Using these criteria, mechanical waves may be separated into three categories, into three classes, into three types: infrasound, sound, and ultrasound. Infrasound, sound, and ultrasound. And identification, strong definition of these three categories is the frequency range. Infrasound is the set of mechanical waves of the frequencies from 0 Hz up to 16, 20, something like this, Hertz. Sound, it is the set of mechanical waves of the frequency frequencies range from 20 Hz up to 20,000 Hz. And ultrasound starts from the frequency of 20,000 and greater thousand Hertz. So you can see what are that three categories. And just sound is heard, is the audible frequencies range for the human ear. So, and now we start the second point of the lecture. It is just the ultrasonic scaling. It is just the ultrasonic scaling. Technology. We will consider three modes of the technology, but before we start to do this, let's recognize how sound, ultrasound is produced, what are at least but not at last two possibilities for this. Ultrasound can currently be produced at frequencies as high as somewhat more than 10 to the power 9 Hz. It is widely used as diagnostic, therapeutic, and surgical tool in medicine. The ultrasound generator is a device basically consists of a sine oscillator and transducer. The sine oscillator generates high frequency, more than 20,000 Hz electric power, while the transducer unit converts the electric oscillations into mechanical ones. The electroacoustic transducers used in the ultrasound range operate on the basis of various phenomena. In particular, piezoelectric mode is one of ultrasound generation. This mode is illustrated by this diagram. Look here. If pressure is applied to the surface of appropriately cut plates or discs of certain monocrystals, for example, it might be quartz, electron charges are generated. This is the direct piezoelectric effect. This effect is reversible. That is, if electrodes are placed on the crystal plate, the potential difference is applied to the electrodes. The plate will be deformed by the electric field. This is inverse piezoelectric effect. In alternating electric field, the thickness of the crystalline plane follows the variation of the electric field. That is, the crystalline vibrates, producing ultrasound. And one more possibility to produce the ultrasound is the magnetostrictive effect. Magnetostrictive materials exhibit similar behavior in an applied alternating magnetic fields. Excuse me. Field. Both types of transducers also act as receiver, since the mechanical vibrations produce electric and magnetic fields that can be detected and used to monitor incoming ultrasound waves. So, and now look here. What are the medicine fields where ultrasonic ultrasound is implemented into? It is the diagnosis, physiotherapy, surgery. And what are the intensities of the ultrasound? You can see what are the intensities, and the largest intensity is required for the surgical operation. For example, of the destroy of the breaking down the stones, in particular into the liver. And you can see what are the exposure times for that or another procedures. And what are the effects provided by that kinds of the ultrasound? At the diagnosis, nothing at all. The effect is the negligible, but physiotherapy, it is required the deep heating, and the tissue damage, it is the procedure to implement that is done, is provided by that kind of the ultrasound within this time of the exposure. And the next, you can see here the varieties of ultrasound scans that we review just now. What are these? Look here. These are A scan, B scan, and Doppler technique. So these are varieties of ultrasonic scan modes. And let's start from this first, the A, amplitude scan. This is essentially a range measuring system. It operates by recording time T1 and T2 in this particular case taken for an ultrasonic pulse to travel to an interface in the body and be reflected back. The A-scan, echolocation principle of measurement of human body structure size, is illustrated at this diagram. See here at this formula. Is the symbol for the ultrasound velocity. As I said already, it is about 1,500 meters per second for inside of human body. For inside of the human body, meaning the soft tissue, the ultrasound falls onto and reflects through. And look how the A scan is provided. Look here. The short ultrasonic pulses are transmitted into the body, and their returning echo pulses are applied to the white plates of the cathode ray oscilloscope. Reflected surfaces in the body are represented on the CRO as vertical peaks. You can see this cathode ray oscilloscope screen, and these reflected signals are represented here as these kinds of peaks that are in correspondence to the interfaces the ultrasound reflects from. The amplitude of a peak represents the strength of the echo. The position of the peak is determined by the depth of the reflecting surface and the time base used on the CRO. The A-scan is used to measure the diameter, in particular, of the fetal head providing an estimate of the length of the gestation. The A scans are also extremely beneficial in cataract surgery, as they enable the ophthalmologist to measure, look here, to measure distances within the eye, and in particular to determine the power of the intraocular lens needed for the artificial implant. So you can see this mode as a scan. And look here, it is the block diagram of the A-scan system. It is the block diagram illustrating how the A-scan system works. Look here and follow the description I give you. The rate generator, this starts from here, initiates the A-scan system work. This sends applies proper voltage at regular intervals to activate simultaneously the transmitter, the time-based generator, the time gain compensator. Note, by this means the time measuring instrument, that is the cathode ray oscilloscope, is synchronized with the transmitter-receiver system. The transmitter voltage stimulates the piezoelectric transducer to emit into the body the ultrasound short sharp pulse of a few microseconds. The time-based generator supplies a voltage across the X plates of the cathode ray oscilloscope, so that the spot starts moving steadily across the screen. The time gain compensator, it is very interesting. Its role is to control the exact amplification, that is, the gain of the returning signal. The reason is that due to attenuation of ultrasound pulses in the body, echoes from deeper interfaces tend to be very weak. These weak signals might contain valuable information. To ensure that they are not lost, they are amplified more than those originating close to the probe, using the time gain compensator. This increases the gain of the receiver with time at appropriate rate. This technique is known as time gain compensation. A voltage is generated in the transducer probe whenever an ultrasound reflected pulse is returned from the patient. These voltages are amplified at the receiver and applied to the Y plates of the cathode ray oscilloscope, causing a vertical deflection of the moving spot. A vertical line thus appears on the screen each time an echo returns to the probe. The position of these lines on the screen, these 1, 2, 3, 4, 5, correspond to the positions of the associated reflecting surfaces in the body. 1, 2, 3, 4, 5 body surfaces. And let me pay attention that a scan only gives one-dimensional information and therefore is not useful for imaging. For this, the B or brightness scan was developed. In the brightness scan, the echo signals are not applied to the Y plates of the cathode ray oscilloscope, but instead are used to control the brightness of the spot on the screen. Hence, the static B-scan displays the range of reflecting surfaces using spots whose brightness give a measure of echo amplitude. Not the peak amplitude, but the spot brightness measures the echo magnitude. The time base is applied to the Y plates. This produces a static B-scan as it is shown in this diagram. On its own, the static B-scan is not very useful. However, it forms the basis of several invaluable scanning systems and is now by far the most commonly used mode. The simple sector scan is one of the scanning systems implementing the B-scan principle. In the sector scan, the probe is rocked on the patient so that the ultrasound beam sweeps through a fan-shaped sector of interest, rather like sweeping action of a windscreen wiper on a car. A series of static B scans like CD shown in diagram is thus obtained with the time base moving around with the direction CD on the scan. During a sweep, data for each static scan is stored so that gradually a two-dimensional image of a sector or wedge through the patient is reconstructed. Such a cross-sectional picture in plane of scan is sometimes called a tomograph, and the associated study is termed as tomography. The B or brightness ultrasonic scan mode develops two dimensions image of human inside structures. The B scan is essentially a white or black image. Strong echoes produce white areas, while echo-free regions are black. Fluid-filled structures like the gallbladder produce large echoes from their walls, which consequently appear white, as it is illustrated here at A photo. In the B scan photo, the contrast between the light appearance of the diaphragm and the liver tumor, strong echoes, the gray liver tissue, some echoes, and the black cross sections of normal blood vessels, no echoes is clear. You can see this B scan that is essentially a white and black image. The simple section scan suffers from the need to have extremely skilled and experienced operators in order to get clear images. Furthermore, it provides a relatively poor quality focusing, so it has now largely disappeared from the routine hospital work. However, its advantage of only requiring a small entry window or footprint makes it suitable still for particular applications, like imaging the infant brain through a space component bones of the skull. Most hospital ultrasound scanning now uses real-time imaging, enabling doctor to observe events live and as they happening. This relies on the use of multiple element transducers, in which arrays of often hundreds of piezoelectric transducers are arranged in the probe head. And look here, where you can see illustration of not illustration, but it is the introduction, it will be better to say, of the Doppler scanning systems. All of the systems considered so far have used pulse echo techniques, relying on the range finding capability of short, sharp pulses. In contrast, Doppler systems monitor the velocities of moving structures by detecting frequency changes in reflected signals. In particular, in the echoes from moving reflectors in human body. They can therefore employ either continuous or pulsed waves. Doppler scans are often used in conjunction with standard pulse echo imaging. The instruments available ranging from simple pocket-size version giving audio outputs only to sophisticated color flow machines consisting hundreds of costing hundreds of thousands of pounds. This is just the illustration for the principle of blood flow measurement. Blood flow measurement. The Doppler shift technique may be used to estimate the velocity of blood flow in veins and arteries. Since these are generally superficial, veins and arteries, attenuation is consequently less important than with deeper structures, and higher ultrasound frequencies in the range between 5 and 15 megahertz are used given better resolution. Even at 15 megahertz resolution is no better than 0.1 millimeter. Since individual red blood cells have diameters of about 6 micrometers, only the scatter from the clumps of cells can be identified. The diagram illustrates physics principle of blood flow measurement by the Doppler shift technique. Using either continuous or pulse wave Doppler system, the ultrasound is directed toward the sample. The Doppler shift in frequency, delta F, is given by formula shown at the diagram in the correspondence with the component of the blood flow in the direction of the ultrasound beam. This formula. So blood flow in correspondence with the direction of the ultrasound beam. Blood flow velocity. The velocity of blood is thus computed and its variation with time shown on a spectral Doppler display. Look here, the region of interest is first imaged using a conventional pulsed wave B scan. First of all, the region of interest is visualized using the conventional pulsed wave B scan we considered. A particular vein or artery is identified and an on-screen cursor is aligned with the direction of flow. With the direction of flow, the cursor, you can see this cursor is aligned with the direction of flow. The angle theta between the ultrasound beam and the blood flow is automatically computed. Add the photo, the carotid artery in the neck B scan is shown. Carotid artery, so is shown here, this artery. And the color shows this is reconstructed by the B scan. From this, it is clear where the artery divides, there is some narrowing leading to unwanted reverse blood flow toward transducer. The color Doppler display indicates this in red. This flow is colored and displayed. So, and then you can see here velocity is computed by that means, and here let me show the continuous wave Doppler system block diagram. And this principle for the measuring the velocity of body structures, just the block diagram just for this. The transmitter provides a continuous voltage output of constant amplitude and frequency being about from 2 to 5 MHz. Transmitter, the first, starts from the transducer contains separate transmitting and receiving piezoelectric crystals. This is necessary when using continuous waves to avoid the inevitable confusion arising if a single crystal tries to emit and receive signals simultaneously. The receiver outputs signals containing the same frequency as the transducer due to the stationary reflectors, the Doppler shifted frequency due to the moving reflectors. The demodulator mixes the output frequencies to generate the Doppler shift separately, and the filter removes any frequencies other than Doppler shift frequency. The amplifier further amplifies the remaining signal. The recorder analyzer may simply be the ear using headphones or a loudspeaker, since typical Doppler shifts lie within the audible range. Certain Doppler shifts have a characteristic sound. For example, the fetal heart Doppler shifts sound like galloping horses. The placenta like a wind rushing through trees. The experienced ear can recognize any abnormalities of the Doppler shift's sounds. On the other hand, the Doppler shifts, delta f, can be converted directly into velocity using that equation that were shown. With the help of the fast electronic analysis and cathode ray oscilloscope display, the fluctuation of velocity with time can be displayed directly in the form of the graph or sonogram, also known as spectral Doppler display. Positive values of Doppler shift indicate the reflectors moving toward the probe, whereas the negative values show the reflectors moving away from the probe. The trace shows the variation in blood velocity with time in carotid artery in this at this photo. At that position of the cursor that was shown. In practice, you can see here, not all of the blood moves with the same velocity. Since frictional resistance reduces it to lower values nearer the vessel walls. Also, the flow is not always parallel to the blood vessel axis, and hence a range of velocities is recorded at each time instant on the display as it is shown at the display photo. You can see this slowing of the blood flow because of the friction at the blood wall, at the vessel's wall. At the center, the velocity is the greatest. So, and you can see not in all position within the blood vessel, the velocities of the blood particles are parallel to the axis of the vessel. The spectral Doppler display shows the distribution of the velocity of the blood structures into, as it is shown, carotid artery. It is true for other vessels as well. And this is just the provement. Look, pay your attention. It is the provement of that as the friction between the vessel's wall and the blood structures, slowing the motion of the blood. And from this, you can see, and take the a list of the ultrasound advantage and disadvantage, and these two complete the brief review of ultrasonic scanning modes. And look what else should be considered, and we do this the only as the review. Let me not tell you about the anatomy specificity of the ear structure, but let me pay attention to these physics aspects of hearing. First of all, look here. The sound waves are produced by vibrating objects which cause alternating phases of compression and rarefaction in the medium surrounding the objects. The compression and rarefaction spread out as a mechanical wave, you know already. The range for human hearing is approximately 20,000 Hz. The range of the average speaking voice is approximately 2,500 Hz. And this is just the ear frequency response, intensity response. The human ear can comfortably respond to intensities from this threshold of hearing, the lowest required for feeling of the sound, for feeling of the hearing, up to one that is considered as the threshold of the feeling, threshold of the feeling. And measurements of auditory response are somewhat subjective characteristics, but two objective characteristics have been fairly well established. As I said already, this threshold of hearing is the minimum intensity that is just audible at a given frequency. The human ear is most sensitive for the frequencies near 3,000 Hz. This threshold of feeling at this high intensity, a tickling sensation is experienced when the ossicles vibrate so strongly that they strike the middle ear wall. Its largest magnitude corresponds to the frequencies near 3,000 Hz. This threshold of feeling is frequency dependent as well as a threshold of hearing. So, and this diagram shows you illustrate the mechanical waves range of comfortable hearing, hearing. So, these mechanical waves are of two characteristics, frequency and intensity. And look, because of the wide range, because of the enormous intensity range of the ear, it is common to measure intensities in logarithmic units or decibels. The intensity level, beta, relation to the intensity is shown by the formula at this diagram. This formula creates the logarithmic scale to measure intensity, to measure the intensity level relatively to the threshold of hearing, relatively to the 10 to the power minus 12 watt per meter squared. And look here, you can see the illustration of this. Loudness is a subjective sensation and so has to be measured subjectively. Since loudness is frequency dependent, measurement must take this into account. In phone measurements, all sounds are referred to a standard frequency of 1 kHz. In order to measure the loudness of an unknown source, the following procedure is followed. The source to be measured is placed near the standard source, whose intensity is adjusted until the two sources have equal loudness. If a standard source has an intensity level of 1 decibel, then the loudness of the unknown source is 1 phone. Loudness is dependent on intensity, but is also a result of the energy transfer characteristics of the ear. The ear's logarithmic response to intensity Changes is the example of the Weber-Fechner law, which states that the change in the perceived property is proportional to the fractional change in the stimulus. It is common to a number of stimuli, including weight and brightness. Loudness is measured in phone and is strongly frequency dependent for a given intensity. Here you can see the curves of the same loudness. This curve for the frequency range of the loudness of 40 phones, but you can see different mechanical waves should be of different intensity to produce the sound we perceive as the sound of the loudness of 40 phones. So, and look, unfortunately, we should stop now. And what is the next? It is, as I said already, the description of the specificity of the anatomic structure of the ear, and this you can take, look here. This you can take from, now let me stop a little and say this. Let's conclusion. Physics methods as ultrasonic scanning are objective, evidence-based diagnosis of human body structures state. Acoustics theory is evidence-based in terms of the feasibility and necessity of analyzing sounds by frequency as a parameter that uniquely identifies sound sources. Biomechanics theory quantifies the processes involving the structures of the outer and middle ear that increase the sound intensity, followed by the development of auditory sensations. And look, it is the bibliography list. You can see, including the internet resources. And finally, here you can find the audio recording of the lecture. You know this, it is the unit 2, and the lecture option is included, and you can go there to obtain the video recording of the lecture as well as the notes of the lecture material that is represented, that was represented just now. Thanks for your attention. We finish.